Take it away.
Thank you very much. Thank you for the invitation, thank you for the hospitality, for organizing this wonderful gathering. Do we have a pointer? No? Okay. Okay, let me take it away. I have many things to say, and I will try to put everything in the appropriate perspective. Here, probably if you ask questions, I will take small deviations to account for that, provided time is available. Okay. Needless to say that one of the most central features of quantum mechanics, if not the central feature of quantum mechanics, is that in general, physical systems don't have definite values of their attributes. Those attributes that normally in classical context serve to describe the system. There are few exceptions to that, except when the system is an eigenstate of a certain operator, then we take it to have for the system to have a definite value, but generically we don't have the states of a general system are not eigenstates of most operators, and then besides their, let's say, expectation value, one talks about them having quantum uncertainties, sometimes called quantum fluctuations. And I think this is a very unfortunate word that has been chosen because it leads to a lot of confusion, perhaps not here, but certainly in certain circles, especially among cosmologists. Which the fact that the same word is used to describe both these quantum uncertainties and variations, things like variations of values, definite values over an ensemble, or variations of a certain quantity characterizing an extended system, for example, the surface of the sea. We use the word fluctuation to refer to all of these together, and the fact that we use the word fluctuations shouldn't be taken as license to pass from one interpretation of the word to the other. Okay? So in order to emphasize this very simple point, let me just point out, let's take, for example, the ground state of the harmonic oscillator. The ground state of harmonic oscillator is in position variable, is characterized in part by two numbers, its expectation value and its quantum uncertainty. And often people, as I said, take this to mean that somehow the system can be taken as jumping from one value to the other. Or thinking that somehow this is meant to represent an ensemble of systems and not each individual system, which would leave us with the question, how do I represent an individual system, which is particularly important when we are talking about the universe, where we have access, or we are interested in just one of them. It is, of course, true that if I decide to measure this value and produce a very large number of copies, of identical copies of the system prepared in a similar, in identical way, I will obtain an histogram of values given by that, and the larger the number, the better the fit to the Gaussian. However, we have to remember that in going from the previous graph to this graph, in which I now have actually a histogram and each individual system now has acquired a relatively definite value of the quantity that was previously indefinite, has occurred due to the fact that we have done violence to the system. We have come into the system with something external, modified the system, the state of the system dramatically. Probably in the case of the harmonic oscillator, we had to inject energy because the energy of each one of these states is higher than the ground state by definition. So a measurement was involved in going from one to the other. Quantum fluctuations play a role, an important role in at least three aspects of our current account of cosmology: the emergence of the seeds of cosmic structure during inflation, the generation of primordial gravity waves during inflation, and another problem that afflicts many concrete inflationary models called the problem of eternal inflation. And as we saw in the previous example, we have to be careful in avoiding identification of these quantum fluctuations with stochastic fluctuations. Because, as we said, that can be justified only if something like a measurement is involved in ordinary quantum mechanics. Of course, there are modified versions that address the measurement problem, but we are forced to face the measurement problem in a context, in the cosmological context, where this problem becomes particularly exacerbated. Becomes exacerbated simply because there is no candidate, not reasonable candidate for an observer, for a measuring device, for anything like that, if we are going to talk about the early universe. By the way, I have decided that the measurement problem is such an important problem, we should call it from now on the M problem, taking lessons from marketing of some other programs. Okay, sometimes one says, well, forget about all these philosophical subtleties and just identify the quantum fluctuations with stochastic fluctuations without paying too much attention. This is actually a very dangerous thing to do and can lead in some situations to drastic conflict with experiments. It's not only philosophical niceties, but you can get really in trouble. One example on which we have been working lately is given by the electric dipole moment of the neutron, where the quantum uncertainties can be estimated to be of that order, 10 to the minus 14 electron centimeters, while current experiments are setting bounds that are at least 10 orders of magnitude stronger. If this electric dipole moment was jumping around the values within the uncertainties, it would be impossible to get something, a result like that. Okay, so back to our topic, cosmology, in particular cosmic inflation, which is, as we all know now, part and parcel of our best cosmological models. Cosmic inflation corresponds to early stage of the universe in which the expansion rate accelerated, basically becoming something very close to the Symmetry universe. And this accelerated expansion is turned off after at least something of the order of 60 e-folds, perhaps even more. So it's a very long period in let's say, conformal time during which this dramatic accelerated expansion occurs. The theory is described by the simple action that the Hilbert-Einstein action for relativity and a scalar field where the scalar field is varying very slowly and is only a function of time, essentially, and therefore this potential acts essentially as a cosmological constant, explaining why we get a result that is so close to the Symmetry universe. In a way, the resulting dynamics of this accelerated expansion drives the universe into a condition that is extremely homogeneous and isotropic, where all matter content has been diluted, in particular all defects or remnants from early phase transitions. That was one of the reasons for the invention of inflation. These are exponentially diluted, and that's one of the important features of inflation. It also drives the universe towards an extremely spatially flat condition. It's another one of the successes of the story, but the biggest success is supposed to be the account for the emergence of the seeds of cosmic structure out of the quantum fluctuations present in the early epoch. However, this account is quantitatively extraordinarily successful, but at the conceptual level has a serious difficulty that can be addressed by various proposals to different degree of satisfaction depending on your taste, but it's clearly a serious problem if you just take quantum mechanics as we have it, because in particular that situation is completely homogeneous and isotropic, and out of something that is completely homogeneous and isotropic due to this accelerated expansion and to the dilution of everything that was there previously, we are supposed to have the seeds of structure which are primordial anisotropies that eventually will grow due to gravitational to the gravitational interaction and become galaxies and stuff like that. So how does the analysis go? Let me do a very schematic account of that. One simply writes the metric of the space-time, considering the essentially homogeneous and isotropic expansion, and adding the potential of having small deviations in the metric represented by the so-called Newtonian potential, and let's say the tensor modes represented by Hij. I don't have a pointer, no? It's okay. The normal account of this story starts by separating the scalar field, the inflaton field, into a part that, as I said, is homogeneous, depends only on the conformal time, and a possible small fluctuation that is supposed to contain the possible time space-dependent parts. And the same is true about these perturbations of the metric, which are the three items in the story so far that could contain spatial dependencies. The background, this normal story is, the background is treated classically, both the scale factor and the inflaton potential, and is assumed to be in this setting, in this condition that is called the slow roll regime, where the solution is for the scale factor is basically a de Sitter type behavior, which in conformal time is written in that way. It's conventional to set A, the value of the scale factor, equal to 1 today, and then this parameter eta during inflation goes from a large negative number to a small, relatively small negative number. The interesting part for us will be these perturbations, which I said contain in principle all the spatial dependent parts, but they are assumed to be, they are treated quantum mechanically, and they are assumed to be characterized by a vacuum state. The idea is that, again, why the vacuum? Because as inflation would dilute all pre-existing features, and all other fields present in the universe are equally driven to the vacuum and are not even written here because of that. But we are told the state of the quantum field is also characterized by the quantum fluctuations or uncertainty, and then we face one of these instances of serious confusion in which we take these quantum uncertainties, quantum fluctuations, as if they were stochastic variations. The field is supposed to take some values here, some other values in some other parts, and those are supposed to be the seeds that will eventually grow into the structure we find in our universe today, and which whose first traces can be seen in the cosmic microwave background. But as I said, the universe, according to this picture, is at this stage completely homogeneous and isotropic, including these so-called quantum fluctuations. The state itself is all there is. The quantum state is all there is to the quantum system, and the state can be shown to be invariant under translations and rotations in a very simple calculation. So despite the fact that there are uncertainties, the state itself is symmetric. Exactly the same way that the harmonic oscillator, despite having a width, has the symmetry x goes to minus x. So the big question is, how do we get actual seeds of structure if the dynamics of the closed system does not break the symmetries? And here we face this cosmic Schrödinger cat, which I like to say was present somehow at the early universe, and like the Cheshire cat eventually is gone and leaves us only with certain traces from which we are supposed to deduce or make a reasonable story of what happened. And those traces are, of course, the CMB and the large-scale structure that we have access to. Okay, so how are we going to approach this? As I said, there are many ways of approaching it. We are going to consider collapse theories. Why? Because collapse theories have the possibility, have the feature that is able to take a symmetric system, a system containing a symmetry, into something that is not symmetric, even though the dynamics is in principle symmetric. That is due to the stochastic nature of these theories. Collapse theories, on the other hand, involve a modified evolution, time evolution or space-time evolution, if you're talking about the quantum field, of the quantum system, and therefore we need to have the notion of space-time. That, together with the fact that when we look at the situation regarding quantum gravity, we have to recognize that despite the interesting progress that our colleagues involving the various programs have done, we don't have at this time a reliable, solid theory of quantum gravity that we can use methodologically in a methodologically transparent way to deal with the problem. So we are going to treat space-time classically. The reason for this is that not that we believe that space-time is ultimately classical. Space-time probably is, as everything else in nature, quantum mechanical in nature, but if we are far away from the Planck regime, from the regime where curvatures are of the order of the Planck scale, by that stage, a classical description should be an appropriate approximation. After all, any successful theory of quantum gravity should be able to connect from that regime, that very complex regime where perhaps space-time is not even present, should connect down to general relativity if it's going to be successful, and in the path of making this connection, there is going to be a regime in which semiclassical gravity can be expected to be at least approximately valid. Again, as long as curvatures are not extremely large. Moreover, our best theories for the description of gravitation are GR. This is a solid theory. We know we can trust it. We know we can have been tested by now a very large set of regimes, and we can rely on that. The same can be said about quantum field theory, and it's not naturally it can be extended to quantum field theory in curved space-time. So the idea is we should put these two things together, work with these two things together, and see where can it lead us if we try to address this problem. Dealing with that, doing semiclassical gravity involves dealing with very problematic aspects. In particular, generically speaking, we will have, well, we will have an expression like that connecting the Einstein curvature of the classical space-time metric to the expectation value of the energy momentum tensor. But if we have collapses, we will have generically evaluation of the divergence zero of the right-hand side. So this equation cannot hold during a collapse. Then we have to find a way to do that. Well, we have been developing a scheme to do that. The idea is that there will be regimes in which this semiclassical gravity is assumed to be valid. Basically, like hydrodynamics is valid in most situations. Then there will be situations where something dramatic happens, like when in hydrodynamics, let's say you form cusps or you form foam or something like that, which falls outside the theory. That would correspond to a situation in which a collapse occurs. After that, you return to a situation in which you can use hydrodynamics again, and that's the scheme we have been using. For that, we have used this so-called SSC formalism, in which you can imagine two regimes in which the space-time is divided in the regime prior to a collapse, which is described by precisely a quantum field theory construction on a curved space-time with a state satisfying this expression, and the transition to a second regime after a collapse that we take to have occurred in this hypersurface, a transition to a second situation where which is described again by a second type of construction of this sort. This involves many, many complications. Let me not get into them because I'm sure we are going to run out of time. Anyway, when we do this, we follow this path, which, by the way, as I said, semiclassical gravity involves treating all matter using quantum field theory in curved spacetime and all gravitational degrees of freedom in classical terms. Therefore, we will quantize the zero mode of the inflaton, which is normally not quantized, but we will not quantize the metric perturbations. So no Mukhanov-Sasaki variable for us here. Regarding the vacuum, we will have basically a slow roll condition for the expectation value of the zero mode of the scalar field and basically the standard inflationary behavior for the scale factor. And the interesting thing, of course, are the modes that have the non-zero modes. And for the non-zero modes, we will now the calculation that I'm going to describe is an effective calculation that we have checked in simple situations produces the same results as this more rigorous scheme that we have constructed for the general problem, but has been used here with an effective procedure, practical procedure that, as I said, produces essentially the same result. So, regarding this scale different from zero modes, or the space-time dependent modes, the field and its momentum conjugate are characterized by wave functions that are centered at the zero, both in momentum and field space, and of course by quantum uncertainties. And the metric perturbations are not excited, the perturbations are zero, so we have a completely homogeneous and isotropic situation. Then a collapse will modify, a collapse that of the quantum state of the field will modify the expectation values of these quantities. And we will assume that the collapse occurs mode by mode. And of course, the universe will correspond to one particular realization of the stochastic dynamics that represents the collapse. But the moment these quantities collapse, I substitute now in the perturbed semiclassical Einstein equations, and I obtain this expression, for instance, for the Newtonian potential. Okay? So we see that the Newtonian potential, which would be the place where the scalar perturbations that form structure are encoded, and the thing that we are supposed to detect in the CMB, was zero before the collapse occurred, because the expectation value of these quantities vanishes in the vacuum state. But after this state has changed, this quantity changes. Now we have a non-zero value, and then we have an excitation for the metric perturbation. And that's how we account for the emergence of primordial inhomogeneities in the universe. Okay, let me not get into details. When you use a collapse theory, you need to choose the collapse operators. Here we were guided by dimensional considerations, and also a little bit by what we knew the result that we need to obtain had to be, and choosing those as the collapse operators, which at this point we don't know why is this the correct choice. This is the theory under construction. All this program is under construction. We don't have a final theory. Let me announce that loud and clearly. You get a spectrum that is essentially, basically the same prediction that you get in standard accounts of inflation, but now with a clear picture that you can even state in words. How did these inhomogeneities occur? Well, there were some collapses that destroyed it. Anyway, this helps setting, then making some standard assumptions about the inflation, what is taking the the grand unification scale for the scale of the inflaton potential, and taking standard values for the duration of inflation, etc. One obtains a value for this parameter, which is the value of the collapse parameter, and it's interesting to see that it's not very different from the GRW suggestion. This is something just interesting. I should note that other people have done other calculations choosing different operators, and they have obtained different results. So this means that on the one hand, you know, the predictions that we are making at this point are not robust, don't work for any choice of operator, but it means that we can learn from cosmology which are the operators that in this stage can work and produce the right thing. Okay, but at this point we have just learned something about what the collapse theory should be. Now let's see if we can do something else. Let's now take the lesson and apply it to the tensor modes. For the tensor modes, we have the semiclassical part of Einstein's equation again. Note that we don't quantize the metric perturbation. Therefore, if they are going to be excited, it's because there is a source term, and the source term that appears in the left-hand side in the energy momentum tensor is that one that you see there. You see that it's now proportional to the square of the perturbations, rather than linear in the perturbations as the previous one. You can solve this, let me go into momentum to Fourier transform, blah, blah, blah. You can solve these equations, and now you substitute what you have learned from what works in the case of the scalar sector, and now you produce a spectrum for the tensor perturbations. This spectrum for the tensor perturbations is dramatically different from the standard prediction. The spectrum for the scalar perturbations, we, if you want, adjusted it a little bit to obtain the same predictions as this. But then we are forced to conclude this other spectrum for the tensor perturbations. And this spectrum that has two important features that I should emphasize. Look, first of all, it's quadratic in the potential, in the inflatonic potential. And second, it has a different scaling with wavelength, different k dependence. And this thing ensures that the prediction that we make for gravity waves is completely different from the prediction that you obtain in the standard account. So the prediction of the standard account is the red line that you see over there. And as you know, this has created a lot of problems for many inflationary models, because people have looked at, for these primordial gravity waves to no avail. None of them have been observed. And the region in which the searches are occurring is this region, where you see that we have predicted a dramatic suppression compared to the predictions of the standard accounts. So, in this sense, this program is producing things that are fitting better at the phenomenology that we are living with than the standard prediction. In other words, it's not just philosophical niceties that are involved. Okay, let's go to the next problem. How am I doing on time? My chairman.
Yes, so 20 minutes left.
Yeah. Okay, eternal inflation. One of the most serious problems, and is considered so serious that some of the proponents of inflation have now gone back and looked for alternatives because they were convinced that this is a terribly damaging problem, is that considerations of the sort that are made in the normal treatment of inflation leads one to expect that inflation will never end. How does that work? Basically, the argument goes like that. The inflaton field, or the inflation, is driven by the zero mode of the inflaton, which is in this slow roll condition, but that is the classical characterization. The classical change in this inflaton is to slowly decrease the effective, it rolls down the potential, so the potential decreases, that decreases the effective cosmological constant. However, it is argued that this object should also be subject to quantum fluctuations, and then one compares what is the size of the quantum fluctuations in the characteristic time compared to the size of the classical displacement. Basically, this picture, the thing is rolling down and is subject to both the classical displacement and also to the quantum fluctuations. But look, and the idea then is that if the quantum fluctuations are larger than the classical fluctuations, then the inflaton can move upwards. If it moves downwards, nothing serious happens. But if it moves upwards, the value of the effective cosmological constant will be larger there in that region. The universe will grow faster in that region, and that region will become more dominant than it was originally, and the same story can be repeated. And at the end, the universe is expected to be dominated by the regions in which the motion was up, and inflation, instead of ending, goes up forever. But you see here that this is precisely the same problem that we had before. They have identified these quantum fluctuations, these quantum uncertainties, as if they were stochastic fluctuations. And that's why they can say, okay, the thing will fluctuate upwards or downwards. There is no such fluctuation. There is a quantum uncertainty. Of course, now that we have introduced stochastic dynamics into the story, we now have a reason to have fluctuations, stochastic fluctuations. Stochastic fluctuations produced by the modified evolution which contains these collapses. The collapses will play the role of these stochastic fluctuations. So what we have done is to see within the context of collapse theory, we have asked the same question. How does the classical displacement compare to the now truly stochastic fluctuations produced by the collapse theory? So we have studied this as we saw, okay, so let me now get into some detail. As we saw, I don't know if you remember, in order to obtain the correct spectrum, we needed to assume that the effective collapse parameter was proportional to k. So you in principle you would say, okay, so for k equal to 0, the zero mode, there is no collapse, you have no problem. The problem is that while that's true for the k exactly 0 mode, the modes that have k's that are so small that they are effectively, for the scale of our universe, 0 modes, they are so close to 0, they basically don't oscillate within the, within our particle horizon, let's say. Those modes could, in principle, contribute to this effect. So we have studied the effect of these stochastic fluctuations for those modes that are shorter than, have k sufficiently small, meaning that their scale of the wavelengths are larger than the particle horizon in this case, and we have considered slightly modified version that we ensure that behaves as lambda times k in the regime where the CMB parameters, where the CMB, that are relevant for the CMB, but may have a slightly different value for the as I go to k equals 0. So for the visible values of k, we effectively recover the same behavior as we had before. And in this paper, we studied what are the regimes for which you would both satisfy the condition of obtaining an appropriate spectrum in the CMB and avoid the problem of eternal inflation. And this is a region of the interesting region in parameter space where the parameters alpha and b are there. The region that is viable is the yellow region. And thus we have achieved the following. We have now a reasonable account for the generation of primordial seeds of structure. As a bonus, we have gotten rid of two problems affecting inflationary cosmology. One was the problem of the unobserved tensor modes. The other was the problem of eternal inflation. I mean, it's not that we have gotten rid of that problem. It's that we have shown that it's possible to get rid of that problem. There is a door opening to get rid of that problem. Why should this behavior be like this? I don't have an answer for that, okay? But what is clear is that there is an opening for addressing that problem, and this is done all for one particular simple inflaton potential. We have not studied anything except the simplest one. So, of course, we don't see any evidence of those things directly now, even though people are looking for collapse theory. But just like this other cat smile, I think this is a hint that we may have been looking in the right direction. At the same time, it's clear that we are left with a sense of puzzlement because more fundamental and complete story is clearly called for and needed. So, thank you.
David, please.
So the positive account here is very interesting. I wanted to worry a little bit about the claims of confusion at the beginning of the talk. I mean, of course, physicists say lots of casual stuff, and I'm sure some of it is confused. But if one looks at what's going on mathematically in the standard structure formation derivations, it feels like all we're doing is applying unitary quantum mechanics, starting with a homogeneous isotropic state, evolving into a superposition of individually inhomogeneous anisotropic states, whose superposition is homogeneous and isotropic, running that forward a very long way, and at that point I have a quantum state as a superposition of all of these various ones. The individual evolution of these things is classical, the interference between them is negligible, and at that point, whatever my solution to the measurement problem is, licenses me to say, interpret the multi-squared amplitude as probability, and now I have a probability distribution over individually highly anisotropic, highly homogeneous spaces, and then I compare that probability distribution to data.
Yeah, well, in the way you have stated it, I cannot disagree, is simply this, right? We go from this, which is symmetric with respect x to minus x. If you have an account for how to get to this, it's true. My problem, first of all, is that in most explanations of cosmology, this is not done. You are taking the many world point of view. There are, we know, basically three paths essentially to address the measurement problem. You are taking one. Word here will take the Bohmian approach and if you address the problem successfully, fine. But what cannot be done is address it hand-wavingly, because if you try to do that, then you will have this problem. If you simply interpret uncertainties as things acquiring values in the regime where the uncertainty, in the support of the, of the region where the uncertainty, where representing the uncertainty in the wave function, you will have a very, very hard time accounting for results such as this, where we have a difference between, the spread of the wave function, if you want, in that particular value, and the accuracy of bounds that have been obtained, that is at this point 12 orders of magnitude. Okay, this is a paper we are just putting in the net. We are trying to get it published, fighting with the referee, of course, who says this is obvious. Anyway, that's my point. I will have to agree that if you have a reasonable solution to the measurement problem gives you that, then I am happy.
I mean, I take the point, but in a certain sense, I didn't think I was assuming the Everett interpretation. I was is just shutting up and calculating. I mean, we know that the verbal glosses physicists put on quantum calculations are often confused. What I guess I'm saying is that the actual calculational methodology being used in the orthodox inflation calculations is just unitary quantum mechanics.
Right. I'm saying that if you do the shut up and calculate story with the electric dipole moment of the neutron, you are going to end up in conflict with observation.
That's not actually the calculation. Unitary quantum mechanics doesn't.
This is unitary quantum. Sorry, no. You are doing two things. You are doing unitary quantum mechanics and then telling me this story that you have all these coexisting realities. One of the which our universe representing one of them. If I translate that to the neutrons, each neutron will have one value of this, will correspond to one value of this electric dipole moment of the neutron. You will have a spread of these guys that would be of the order of 10 to the minus 14. You have a large collection of neutrons, and then you would not be able to account for this fact.
But if you've actually shut up and calculated, then you can...
That's a shut up and calculate example in which things go wrong.
This is shutting up and calculating incorrectly. That's not
the question. Why is this incorrect? Why is this incorrect?
Because if I do unitary quantum mechanics and I include the measurement model, I won't get this result.
If
I do unitary quantum mechanics in which I include the measurement device in the process, I won't get that result.
Yes, you will get this. I challenge you to do the calculation here and not get this result.
But if I'm sure you just falsified unitary quantum mechanics, in which case I actually will get it published, but I really doubt it actually has that result.
Okay. No, it's not a question of the scale, it's a question of which operator causes the collapse. The collapse dynamics involves choosing an operator, which in the case of non-relativistic quantum mechanics has been fairly well identified as being the smear position operator. I don't know how to go from that to quantum theory reverse spacetime. I need to replace the position operator by something else. I don't know what is the recipe. Other people have taken other recipes. And when they take different recipes, you can produce rather different results.
Could you say something a bit more detail about how the choice of the collapse operator is related to the results?
Yeah, well, for example, take CSL evolution. CSL evolution tells you that the solution of your evolution equation is time order product e to the integral dt of IH, which would be the standard part, and then you have something like a random function of time times, let's say, your parameter and the collapse operator. This thing appearing square here, I think is the minus, doesn't matter. Acting on the wave function at time equals time t0. This is how evolution occurs in a collapse theory called CSL. And here is the collapse operator. You see that it plays a role almost similar to the Hamiltonian. It's completely determining how the deviation from evolution is. If, for instance, you put the Hamiltonian here, you are not going to obtain a collapse because it's just going to be a factor, an overall multiplicative factor over things. So it's essential what operator you put here.
Okay. Right, so I guess sort of any reasonable choice of class operator should lead to the same prediction, which is that we'll get probabilities over macroscopic universes, the same ones that you would have got from unitary picture because it evolved to the present day and next.
Well, collapse theories have been designed so as to ensure that you get the correct distribution of position of values at the end of the collapse evolution. Basically because people have recognized that when we do experiments in the lab, all our measurements are essentially position measurements. So that's why the position operator, but as you know, collapse theories make predictions that differ slightly from standard theory. And if you choose the collapse operator wrong, they will differ not slightly, they will differ dramatically.
Great, thank you.
I know very little about this internal inflation, well, basically nothing, but what's happening there exactly? Is it like in the situation with the Boltzmann brains that one expects that locally there's fluctuations and eventually it's going to be large enough such that locally it's going to expand? Or
Well, this is more.
There will be a fluctuation and it's...
The problem is not so much that somewhere there will be a fluctuation, is that if the fluctuation occurs in the, I mean, you would imagine that in average, the fluctuations would average out and nothing would happen. Except the problem is that if the fluctuation goes one way, that comes accompanied by, I mean, this is the standard story, comes accompanied by an increase of the effective cosmological constant. So that region where the fluctuation went up will grow faster than other regions where the fluctuation went down. And eventually, those regions will end after 10. So these two things are...
Yeah, but like you gave the example with this Gaussian state, right? So this could be the ground state of the harmonic oscillator.
Right.
And
there is no...
I wouldn't imagine...
No, there you don't have this amplifying thing that will drive in one direction, which is this cosmological.
Yeah, you wouldn't have.
No, you wouldn't have. In the case of...
There's interaction with other stuff and there's maybe the coherence and all that, or...
Sorry?
Unless there's interaction with other stuff and that causes the coherence and then, well, like David Wallace was saying, you could have in some branch...
In some branch we'll have... Yeah,
that needs interaction with other stuff.
But you see, my point here is to first object to the statement. Then resurrect the statement after I have brought in this new element. And since this new element is not, fixed once and forever, this new element offers me the possibility of choosing this new element in a way that... But my first step is to object the general argument.
No, I was just wondering how far you can get with ordinary quantum mechanics and still...
Well, let me just state a sociological proof. People that have invented inflation were so upset about this problem. Some of them, Steinhardt, I don't know, and others, that they basically went looking for another theory.
This hydrodynamic reading of the semiclassical equations, right? Is this, I mean, what you were presenting over there, is this somehow linked to other conceptions in this direction, stochastic gravity or so? Is this something...
Well, stochastic gravity has something in common with this. In fact, they have the same problem that we have, except that they have not recognized it. In stochastic gravity, what you do to take into account, they do this. So this is not what we do. This is what they do. So they write 8 pi g T mu, and they add a stochastic function, classical stochastic function of x, which is chosen so that xi mu x xi rho sigma y ensemble average, the stochastic average of this thing coincides with the corresponding, let's say, quantum fluctuations of the energy momentum tensor. That's what they would call this thing, okay? So this is what they do. The problem is, if you take the stochastic realization, in the average, you can show that in the average they have the zero divergence. But each one of the elements of the ensemble does not have zero divergence. So each one of the elements of this equation is inconsistent. And then my question is, why having a collection of inconsistent equations produce an average, something that I can regard as consistent. We have this problem, and we have chosen to solve it in this way, which I added this thing because there are complications, because you need, in order to do this carefully, you need to renormalize the energy momentum tensor, and that becomes very, very difficult when you are constructing at the same time the space-time over which you are going to renormalize.
Martha, and then I think one.
Thanks. I guess I have a very, very naive question. So, in other approaches, what you have would be symmetry breaking with a phase transition or something like this. So, in this case, can you see this passage from one regime to the other as a phase transition as well, or it's something?
Okay. So first of all, we are not dealing with the thermodynamical system here, right? We are dealing with a quantum field, and what you would have is the type of transitions that you have in quantum field theory. Let's say spontaneous symmetry breaking, something of that sort, right? But spontaneous symmetry breaking, despite the name, is not something that really can be taken to occur as a function of in time for an isolated field. An isolated field, if you put an isolated field in a potential that is like this, and you put it in the ground state, and you evolve this potential, and you make the potential change but maintaining the symmetry, the field is going to evolve into a symmetric superposition and not, sorry. The field, you start with the field, you put it in the ground state of a potential that has one ground state. You now modify the field as a function of time. The state of the field is going to evolve into something like this. It's not going to evolve to either this or this due to the unitary evolution. You can see this by the symmetry of it. If you put something to perturb the thing, then, but by itself, it's not going to get out of there. So you are not going to break the symmetry. I mean, this is a theorem. If you have the dynamics doesn't break the symmetry, and is deterministic as the unitary dynamics controlling quantum mechanics, most of quantum mechanics is supposed to be, then you're not going to break the symmetry. If you add a stochastic feature, then you can break the symmetry.
Okay, this is not a thing, all right?
No.
What is it?
Just because the slide is on about the electric dipole, and I see also weak measurement. And like a weak measurement of an electron, of the spin of an electron can be 1,000, but
Yeah.
there also seems to be incompatible with quantum mechanics as person you don't.
Well, you have to be very careful with this.
It's not what's at issue here, or is it?
No, well, but a weak measurement is what allows you to do this. According to us, according to our analysis, a weak measurement is what is behind your ability to measure this with this precision.
And you can make the analogy that the spin of an electron can be 1,000 measurements, or?
Yeah, well, in the case of the spin that gives 1,000, you do what is called a post-selection spin measurement, right? So the post-selection is there playing a very effective, important role. Here is not being used in that way. Okay. So what we have done is we have looked at the experiments that are producing this thing and see what is happening, and then we realize it's a weak measurement, and that explains why you can do this.
So I'm just interested in just going back to this issue of the Bianchi identity. So you're suspending the Einstein field equation for a moment during the collapse to get around that problem.
Yeah.
And when it starts up again after the collapse, have I changed the gravitational field?
Yeah, you have. Okay, so that's one of the complications that you need to do. If you are going to change and you're going to come from a regime in which semiclassical gravity is valid in this area and is valid in this area. One of the things that you need to ensure is that, for instance, the constraints are satisfied here.
That's what I was thinking, yeah.
So you need to determine how the metric is going to jump from here to here. And there is some choices, because you have 4 constraints. So this is something I should have explained. I thought I had more time. But okay, so you have the 4 constraints, and you have the following quantities that give you, let's say, the geometrical data: Hij, which is the induced metric, and Kij, which is the extrinsic curvature. So these are 6 and 6, 12 total things. We have 4 constraints. So we need to, in order to specify, to have a clear recipe, we need to do something with that. The first thing we did is to take an analogy of what happens when, let's say, you hit a ball. When you hit a ball, things are discontinuous. The velocity is discontinuous because, well, it's not that it's truly discontinuous. It's discontinuous because you have chosen to describe the hitting of the ball as occurring instantaneously. And in reality, the ball is hit, deform, and then starts accelerating. But you have chosen to compress this into a thing, then the velocity is supposed to change instantaneously. The position is not, because the velocity is a derivative in better. So by the same thing, we decide that this remains unchanged. So one of the conditions is that there is no jump in H. Now we have this other guy, and this guy can be decomposed canonically. I want to decide what is the jump in Kij. The jump in Kij can be decomposed canonically into something like di dj minus 1/3 d square hij times a plus hij times b plus dicj plus djci, where dici is equal to 0, plus lij, which also is transverse traceless. So this is a canonical decomposition of a 3×3 metric. And here we have, let's count the degrees of freedom. So we have 1 degree of freedom here per point, 1 degree of freedom here, 2 degrees of freedom here because of this constraint, and 2 degrees of freedom here. These degrees of freedom are connected to gravity waves. So our assumption, and this is an assumption, is the collapse will occur in a way to minimize the generation of gravity waves. You will not generate more gravity waves than absolutely necessary. That means that you demand that this guy vanishes. So the jump in the generation of gravity waves during the collapse vanishes. That's an assumption. And now we have 4 degrees of freedom that we match here, and then you have enough data to evolve. By the way, this choice played an important role in my conclusion that there were, suppressed gravity waves.
So that's one of the degrees of freedom that's
Yeah.
So I would expect, just intuitively, if I think about a weak field case, and I do a class, if I just think about a weak field example, so
Okay.
I've got like a superposition of mass here and a mass here, and then I have a collapse and the mass ends up over here. What I can intuitively expect is that the Coulomb, the sort of the inverse square law, piece of gravity, just disappears here and reinforces here, historical constraints.
Yeah.
And if there's any existing gravity waves, they just kind of carry on freely and the gravity wave here doesn't change.
Yeah.
It looks like I probably get that out from this formula.
Yeah, I think that we are trying to follow that intuition that you just described in choosing this selection. I mean, it also helped the counting. I mean, we knew we had to get rid of.
Yeah.
Do you also need to specify a lapse function?
No, you can, once you have initial data, you can choose any lap.
But results are going to depend on that.
No, the results are not going to depend on that. The results are going to depend, of course, in which is the hypersurface that you choose to be the collapse hypersurface, and how the state jump there. But the lapse and shift are not. Then you have basically initial data of GR with initial data for the energy momentum for the scalar field, the quantum scalar field, and then you have, the standard results of
but the lapses, different choices of lapses are going to determine which future hypersurfaces you have, and so where the future collapses will happen.
I know. Okay. Here, this setting is done in the following way. We hope to construct a scheme which would be amenable to any collapse theory. So the idea is, you give me a collapse theory that is designed to be applied in non-gravitational context. This is a recipe to how to adapt the theory to the gravitational setting, including the change in the space-time metric and dealing with this issue. And so your collapse theory, hopefully you started with the collapse theory that was, for instance, special relativistically invariant. You generalize it to a generic curved space-time. And that one is the one that I would apply these to. But I haven't chosen that theory. We want a recipe, a generic recipe.
That theory is not going to determine the lapse function.
No, but if the theory is covariant, then it should not.
Okay.
It should not affect.
The general covariant collapse theory.
Yeah.
Okay.
Yeah. Which we don't.
Okay.
So the aspiration is the theory, you haven't got the full theory, but the aspiration is the theory should be generally covariant.
Yeah.
If it's generally covariant, then the lapse shift
The-
is again generally
yeah.
covariant.
Yeah, but now we don't have such a theory, right? So
No. In particular, the
you
CSL.
can't refer to a background here that roughly this background is.
Well, we wanted to have a recipe. We wanted to have a recipe that, by itself, the recipe is covariant. If you start with a theory that is not covariant, the result is not being covariant. But in principle, if you give me a theory that is covariant, this is not going to break the covariance. That's.
And the calculations you did.
The calculations we did are in a very simple setting where we showed that you reproduce this at the level of perturbation theory in the calculations that we did. It's a very simple setting because of all the symmetries of cosmology.
And then we used the homogeneous background.
And we use the homogeneous background, and we collapse on homogeneous hypersurfaces. Yeah. Yep.
Could we go back to one of these graphs with different lines and prediction of your? Could we go back to one of these graphs where you have to speak the predictions in your way of going about and I think the standard methodology, if I understand correctly.
So I don't know what.
Yeah, should be good.
Am I going for
Yeah,
here?
This, yeah.
Yep.
So, yours is the blue one, right?
Yes, CSL is a blue one. Newton is something we invented. It's basically a version of GRW in which the collapse operator is taken to be the momentum conjugate to the field, because that's what appears in the Newtonian Newtonian equation. So we call it Newton. So those are, so those are two collapse theories.
Yeah.
They don't give exactly the same result,
Right.
but they share the feature of having, a very different scaling behavior as a function of k, and a very highly suppressed. And the very highly suppressed thing is very easy to understand. It's very easy to understand because it follows from this feature, right? Compare equation 4 and equation 2.
Yeah.
Okay, sorry. In equation 2, we have the background inflaton. I mean, this is the perturbation of the 0, 0 component of the energy momentum tensor.
Yeah. Okay.
The 0, 0 component is basically the derivative of the inflaton. Okay.
Yeah.
The perturbation of the 0, 0 component will have one perturbed quantity, you know, and one of the background, because I mean you have a square, right? Then you have. But there are no terms that are linear in the background for the generation of the gravity waves. So equation 4, you see that it's quadratic.
Yep.
So this is going to be quadratic in the collapse. Okay? So the collapse is small, this thing is going to be suppressed.
Okay, so now you have these predictions, right? Let's see different models, so to speak. And so how do you map this on the data? I mean, how much of the data do you already have, so to speak?
Well, no, the data basically is ruling out the top part, I think, from here to here. The things at the order of 10 to the minus 3, if I remember correctly, or 10 to the minus 4. That top part is ruled out, okay. Where that red line is passing. That's ruled out. Okay. People are continuing to push this down.
Okay.
If we are right,
yeah.
And they are able to push it down to this,
yeah.
To 10 to the minus 8,
I see.
You will see primordial gravity waves.
Yeah, okay.
If they see that, we will be very, 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 very happy, of course. The other possibility, which is very interesting, and we have started looking at it, is you see the K dependence is different, and in particular for the Newtonian version, for very, very small L's, which means very large segments of the sky, yeah. We have very high predictions. So if we can look at the sky at those scales with precision of 10 to the minus 2, CSL tells us you would be C. But we cannot do that. Yeah. We cannot do that because our galaxy, you know, blurs most of the things at those scales.
Interesting. So if you have actually an expectation of a time scale when people, you know, push the curve more down?
Yeah, no, I've asked people and say this is, for the moment, this is way beyond, unfortunately.
Okay.
But who knows?
But this is not unthinkable to get there, so to speak.
No, it's not unthinkable, but it's
takes
they need 4 orders of magnitude at least improvement.
Yes, yes.